Charles' law is another of the simple gas law. This one relates the volume and temperature of a gas. And this one was discovered by Charles back in about 1800-ish. So he found that the volume of a gas is directly proportional to its absolute temperature. We'll talk about that in just a minute. So the volume is proportional to the temperature, keeping the pressure and the amount of gas constant. So this is the way we express it. It's kind of a double thing there. So this one's fraction, V1 over T1 equals V2 over T2. Boyle's law was P1 V1 equals P2 V2. It's a lot of letters and numbers in R2D2 and C3PO. So this is very, very important. The temperature, when we're doing anything with gases, has to be expressed in kelvins. You can't use Celsius. You can't use Fahrenheit for sure. Why is that? Well, so here's some Charles' law data where graphing the volume of a gas versus its temperature. And here this is for 1 mole of gas at a pressure of 1 atmosphere. So change the temperature, see how the volume changes, graph the data. Here this is half a mole of gas at 1 atmosphere, and this is 1/4 of a mole of gas at 1 atmosphere. And we see that there is a straight line, and it has a slope, right? But the slopes are different because the amounts of gas in each of these samples was different. What's interesting, though, is if you extrapolate means to draw the line beyond where you have any data, which can be dangerous sometimes. But if we extrapolate, we find that all 3 of these lines intersect with y equals 0, or 0 volume, at negative 273.15 degrees Celsius. Does that number sound a little familiar? To convert from Celsius to Kelvin, we add 273.15. That's where this came from. So that temperature is called absolute 0 Kelvin. That is the temperature at which a gas would have 0 volume. You can't get any smaller than nothing, right? You can't have negative volume. So when we use the Kelvin scale, we don't end up with an intercept in our equation for the line, because it'll go through the origin at 0. No, I guess I don't have any pictures of the graph. Any questions about that while we wait for the train to pass? So this is something you could try at home. Blow up a balloon, not super much, but not super small either, kind of medium. You can stick it in some ice water, and the balloon will get smaller. The volume decreases when the temperature goes down. Take that balloon and put it in some very hot water, and the gas will expand, and you'll see the volume increases as the temperature increases. Why does that happen? Well, when we increase the temperature, the particles are going to move faster because the speed of the particles is related to the temperature. You can think of people walking barefoot on hot sand, right? Like at Reedley Beach. Did you know Reedley has a beach? On the river, but it is beach. There's lots and lots of sand. But in the summer, that sand is really hot, right? So if you're trying to get from the parking lot to the water barefoot, that's where the expression hot-footed came from. You just, run really fast so your feet don't touch the ground very much, right? So that's what the gas molecules do. On a cooler day, when the sand is not hot, you can stroll barefoot and be comfortable, right? So cool temperatures, slow, hot temperatures, fast. The particles are moving around much faster here. So that means they're going to collide with the balloon more frequently, and they're going to collide harder. And so they're going to push the balloon out. That's kind of what I just said. Let's get ahead of myself. The balloon, because it can expand, will keep a relatively constant pressure. The only way for the pressure to remain constant is for the volume to expand. So as the volume gets bigger, then there's more room for those fast-moving gas particles, and we can keep the pressure the same. This is that balloon in dry ice. It shrivels up to almost nothing. And this obviously is a hot air balloon. I remember as a younger person being kind of just like, how does that even work? If you blow up just a regular balloon with air, does it float? No. So this is a balloon full of air that has a hole in the bottom, and it floats. What? How does that work? Is it filled with helium? No, it's full of air. But they've got this big burner here. Huge flames, putting out a lot of heat. It's heating the air within the balloon, which causes the air to expand because the volume gets larger as the temperature goes higher. That balloon is open at the bottom. The pressure inside is going to equal the pressure outside. So the gas is going to expand, which means a bunch of the air is actually going to come out, and what air is left, the particles are going to be more widely spaced, and its density is going to be less. And so by heating it, you make the density of the gas in here less than the density of the gas, the air outside, and just like solids in liquids, something that's less dense than water floats. It doesn't matter what shape it is. It will float. Here, you take a less dense gas, it will float in a more dense gas. I just think that's cool. Let's do a problem with Charles' law. A gas in a cylinder with a movable piston, these cylinders with movable pistons come up a lot in this chapter, has an initial volume of 88.2 milliliters. If we heat the gas from 35 degrees Celsius to 155 degrees Celsius, what is its final volume in milliliters? So on the previous example for Boyle's law, we drew an ugly picture. I'd like to show you a different approach here, and that is making a table to organize the numbers. So we have volume of 88.2. We have from 35 degrees to 155 degrees. And they're asking, what is the volume in milliliters? So I'm just going to make a little table here. What's the first number we come to? 88.2 milliliters. So I'm going to write that down in here. 88.2 milliliters. So that'll be part of one column. Which of the four properties of the gas, pressure, volume, temperature, and amount, does 88.2 milliliters represent? Volume. The volume. So I'm going to call this the volume column. Okay? Has an initial volume of 88.2. If we heat the gas from 35 to 155, so we're going to have temperatures over here. It's starting at 88.2, and it's starting at this temperature, right? So the 35 degrees Celsius goes with this is the starting volume. I'm going to call that row number 1, and I'm going to call the other row number 2. The temperature is going to go from 35 to 155. And we should end up with one empty square. Well, it's not a square, box. And we're going to call that V2. But what do we have to watch out for here? Celsius and Kelvin. Okay, they frequently give you the temperatures in Celsius because that's what all the thermometers are marked in. So they do that a lot, sometimes to trick you and sometimes just because that's how it is. So we need to convert those. So 35 plus 273.15 equals 308. And there would be 0.15, but we're just going to keep the same last decimal place. So this is in the ones place. I'm just going to end this in the ones place. That's 308 Kelvin. And then 155 plus 273.15 is 428.15, 428 Kelvin. Okay? So we're trying to find volume 2. We've got volumes and temperatures. We need the simple gas law that has volumes and temperatures in it, which is Charles' law that we just learned about, and that's V1 over T1 is equal to V2 over T2. So the thing we're trying to find is V2. This equation has fractions in it, which my friend who's a middle school math teacher says is the F word to junior high students, and a lot of other people agree with that. Fractions are hard for people. If you're good with algebra and rearranging equations, you can look at this and rearrange it and write it down. Good for you, right? A lot of the rest of us can't do that. And so when you're rearranging an equation that has fractions, the first thing you should do is get rid of the fractions. Cross multiply. So cross multiplying means that I'm going to take the top of one side and multiply by the bottom of the other side. So V1 times T2. And that will be equal to the bottom of the first side times the top of the other side. Now, if you write V2 T1 or T1 V2, it doesn't matter. So I'm still trying to find V2. It's much easier to isolate it now, because this is why I don't recommend using the density equation for doing anything except actually calculating the density. Because people do crazy things and they think they're solving for a variable and they're actually solving for 1 over, which is very wrong. So we can take this one now. Oops. To get V2 by itself, I'm going to divide by V1. I have to do it to both sides. Those guys cancel out. So you should always show your work, especially with the gas laws. And the very minimum is that you should write out the rearranged equation. And be really careful with the 1s and 2s. They're easy to mess up. And you should identify what is V1, what is T1, what is T2. You don't have to use the table, but identify them on the paper. Now we take them and plug them in. We go over to the table. This is V1. 88.2 milliliters. And we're going to multiply by T2, which was 428 Kelvin. And we're going to divide by T1, 308 Kelvin. Let's cancel out some units. We have kelvins in the numerator and kelvins in the denominator, so the kelvins cancel out. And we're left with the unit of milliliter, which is awesome because that's what the problem is asking us for. 88.2 times 428 divided by 308 equals. The calculator is showing me 122.56, and it just keeps going and going. How many sig figs? 3. So this number has 2 sig figs, but when we convert it to Kelvin, because it's adding, it actually gains a sig fig. Yeah, which is a little freaky, but it's okay. So 3, 3, 3, and 3, this will be 3 and 123 milliliters. On the simple gas laws, we can often ask ourselves, does this make sense, and figure it out. So here we took the balloon from 35 to 155, we made it hotter. Is that going to make the balloon get bigger or smaller? It'll get bigger. And our second volume is bigger than the first volume. So that's a good sign. Doesn't prove that you got the right answer, but it's good. Any questions? So this is a thinking problem. The pressure exerted on a sample of a fixed amount of gas is doubled at constant temperature, and then the temperature of the gas in kelvins is doubled at constant pressure. What is the final volume of the gas? Well, let's think about what happens to the volume if you double the pressure. It gets smaller by the same factor. It gets cut in half, right? So now I've got half the original amount of gas, and then the temperature gets doubled. Does that make it bigger or smaller? That makes it bigger by a factor of 2. So what we end up with is the final volume is the same, because those changes. Oh, thank you. Just seeing if you're actually paying attention. Yeah. I didn't make it big enough to read. Could have looked up there, that's big enough. Yeah, the final volume is the same as the initial volume. The third law we'll talk about is Avogadro's law. This relates volume and amount. The amount is measured in moles, and this is the same Avogadro of Avogadro's number. So he was born the year that the United States became the United States. He died in 1856. He was the first one to formally state this relationship between the volume of a gas and the amount of gas in moles. And they didn't have the unit mole yet, but talking about the number of particles being the important thing, not the mass of it. With liquids, you've got a density, right? And the volume is proportional to the mass. But with gases, the volume is proportional to the number of particles, which is very, very different. So the volume is proportional to the number of gas molecules. So we can express this one as V1 over N1 equals V2 over N2. We count the number of gas molecules using moles. So very, very weird. Equal volumes of gases have the same number of molecules. What the gas is doesn't matter. So you could get data like this from an Avogadro's law experiment. So you're measuring the volume of the gas as you increase the moles of gas that are present. And of course, we're keeping the temperature and the pressure constant. So we get a straight line. The volume of gas increases directly proportional to the number of gas molecules. And if we extrapolate to zero, this predicts that 0 gas molecules would occupy 0 volume. Seems pretty reasonable. Which action causes the volume of a gas sample to increase? Decreasing the pressure. If you decrease the pressure, does that make the volume bigger? Yeah. So, there's a dog. There's a dog. What about decreasing the temperature? Would that cause the volume to increase? No, that's going to make it decrease. How about decreasing the moles of gas? No, that will also decrease. So, I think everybody's played with balloons at some point, right? They're fun, right? Also, really bad choking hazard, bad for the environment. Don't release them into the sky, but they're still fun. So, gas laws can be remembered, directions and things like this, by thinking about what would happen to the balloon. So the number of moles of gas decreases. So I take my balloon and I take some of the air out. Does it get bigger or smaller? It gets smaller, of course, right? What if I take that balloon and I make it cold? It's going to get smaller. It's going to shrink up. What if I decrease the pressure outside? Or increase the pressure inside, which is sort of the same thing, it's going to get bigger. Okay? So here's an Avogadro's law problem. A chemical reaction occurring in a cylinder equipped with a movable piston produces 0.621 moles of a gaseous product. If the cylinder contained 0.120 moles of gas before the reaction and had an initial volume of 2.18 liters, what was its volume after the reaction? So we're going to assume constant pressure and temperature, and we're going to assume that that initial moles of gas in there was the reactant, and then that reacted completely. So it's not that we're creating new things, really. Okay, so we're going to go looking for numbers. So I've got 0.120 moles, and I've got 0.621 moles, and I've got 2.18 liters. And then the question word, what is the volume? So let's make a table and collect those numbers. So the first number I come to is 0.621 moles of gas. So I'll just put that up here in this box. Which of the four properties is that? PV, N, or T? N, the amount of gas in moles. So that's N. If the cylinder contained 0.120 moles, so this is a different number of moles, right? 0.120 moles before the reaction and had an initial volume of 2.18 liters. So this 2.18 liter volume which number of moles does it go with? The 0.12, right? And often those will be close to each other, contained this much before the reaction had an initial volume. So it's important to get these connected in the right way. And so that is volume. Now, some people would not be happy with calling 0.621 moles N1 because it happens second, right? You can solve the problem just fine if you do that, but just so nobody's not happy about that, we're going to call that column, that row 2 and the other row 1. So then this is V2 that we're looking for. So Avogadro's law is the one with N's and V's. V1 over N1 is equal to V2 over N2. Again, let's cross multiply to get rid of the fractions before we do anything else. So the top of one side times the bottom of the other side equals the bottom of the first side times the top of the other side. And it's called cross multiplying because it crosses, right? So from our table, we know we're looking for V2. So I can get V2 by itself if I divide by N1. Do that on both sides. Volume 2 is equal to volume 1 times N2 divided by N1. So volume 1, 2.18 liters. Amount of gas in moles number 2 was 0.621 moles divided by N1, which is 0.120 moles. You should always put the units in the equation. We can see that the moles are going to cancel out, so that's a good sign. 2.18 times 0.621 divided by 0.12. Calculator says 11.2815, and the unit left is liters. How many sig figs? 3. So I'm going to round that to 11.3 liters. Does that make sense? Yeah, it does. Because we started with a small amount of gas, and now we have a larger amount of gas. And so we expect the volume of the balloon to get bigger, because that's like taking a balloon that's partly blown up and putting more air in it. It's going to get bigger. Any questions? Here's another one, a little more complicated. Sounds fun. A scale model of a blimp rises when it is filled with helium to a volume of 55.0 cubic decimeters. When 1.10 moles of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of He must be added to make it rise? Assume constant temperature and pressure. This one's not so obvious. We got some numbers in here, so let's just go ahead and, highlight those. So I've got a volume here, a weird unit that you might feel like you've never heard before. And here's another volume, same weird unit, so that's nice. And then we've got this amount of moles. And they're asking how much more grams must be added. Well, let's collect our numbers in a table and see if that helps out at all. So we've got volume of 55.0 cubic decimeters. The blimp will float when it has this volume. When you put this much helium in it, it has this volume. So these two go together. 26.0 cubic decimeters, 1.10 moles. This is one that could benefit from an ugly drawing. So here's our sad blimp on the ground, and here's the floating blimp. Kind of looks like a fish, but it's got some propeller or something back there. So the floating blimp, it will float when it has a helium volume of 55. So up here, the volume must be 55 cubic decimeters. Down here, when it's sad and not floating, this is how much helium it has, and this is its volume. So 26.2 cubic decimeters, 1.10 moles of helium. Drawing the picture might help you to see that the 1.1 and the 26.2 go together. So let's label the columns here. What should I call this first column? V. V for volume. And the second column? N for number of moles. It's kind of a weird problem, but look, I have this little, table, I guess, and there's one blank. So that's good, because I can use an equation and find one thing. What do you want to call the top row? 2? We'll call the bottom row 1, just because maybe it makes a little more sense in how the problem is set up. So then what we're looking for is N2. So this is going to be Avogadro's law again. V1 over N1 equals V2 over N2. And this time, we're solving for N2. What we're looking for is in the denominator. This is where it's really important to cross multiply. So we're going to cross multiply this. V1 times N2 is equal to N1 times V2. And of course, you might be thinking, why do they give it to us as fractions? Why don't they give it to us after it's been cross-multiplied? Oh, they have their reasons. So we'll divide by V1 on both sides. So N2 is equal to N1 times V2 over V1. Does it matter that we have weird volume units? No, it doesn't. Because we're going to take the one volume and divide it by the other volume, and as long as the units are the same, they're going to go away. So we don't need to mess with them at all. So let's plug our numbers in. We've got 1.10 moles. Volume 2 is 55.0 cubic decimeters. Volume 1 is 26.2 cubic decimeters. But we should write the units in there because I wouldn't put it past the book to give you one of these in cubic centimeters and one in cubic decimeters. And if you don't write them down, you may not notice that they're not going to cancel. But these do cancel. So 1.1 times 55 divided by 26.2. This is 2.30916, and it just keeps going. Moles of helium. That should have 3 significant figures. So, is this the grams of helium that need to be added? No. Is this the moles of helium that need to be added to this guy? Not quite. It's the moles we need to end up with up here. But we already have 1.1 in there. So that's where this one, like, pulls some critical thinking in. So up here, this is the number of moles is 2.31 moles. But originally it was 1.10. So the amount we're going to add is the difference of those. I'm going to erase this down here because I need some space. So the difference would be 2.31 moles minus 1.10 moles which is going to be 1.21 moles, right? How do we turn that into grams? Molar mass from the periodic table. Helium, so we're going to have moles up here and grams in the bottom. Periodic table says 4.003 grams for every 1 mole. So I get 1.21, I'm messing that, 1.21 divided by 4.003. 0.30227. Is that right? It's upside down, isn't it? Again, I'd like to pretend that I did that on purpose, but I didn't. I recognized it and said that I'm going to use that. Mole and grams don't cancel. It's upside down. This is why I really, really want you to use this dimensional analysis of putting in the factors and canceling out the units, especially for stoichiometry, because it can catch a lot of problems. So let's do that again. So I want grams on the top and moles on the bottom, so the moles will cancel. There we go. 1.21 times 4.003. 4.84363. And that also should have 3 sig figs. So 4.84 grams should be added. That kind of reminds me of some of your worksheets. Kind of went all over the place, didn't it? It helps me see your answer if you put a box or something around it, or highlight it or something. Any questions? Oh, it didn't have the answer. Huh.